In this video, we're going to start to look at how Newton's second law applies to this rotational motion. So to do that, let's look at an example here where we have a toy plane that is going in this circular direction here at some radius r. And let's say we're accelerating. So there is going to be some acceleration here, some alpha. And as this plane is going around the circle, there's going to be some tangential acceleration, which means there's a tangential force. Well, that force can be found by mass times the tangential acceleration because it's the only force acting in that direction. So that's Newton's second law of translational motion. And we know that that acceleration in the tangential direction is equal to r times alpha. And so if we have the angular acceleration multiplied by the radius r, that gives us our tangential acceleration. Well, we can convert this force in the tangential direction into a torque by saying that that is Ft times r. So really this Ft is torque divided by the radius. So this is really tau divided by the radius here is what we have in this Ft. And when we do that and we solve for tau, we get the torque is equal to this mr squared quantity times alpha. Now this mr squared quantity is a special quantity that we will now call the moment of inertia. And we're going to give it the label of I. So moment of inertia is a funny little thing. And it basically, just like we have inertia in translational sense, it's a tendency to not want to accelerate, not want to change its motion. So something with a greater mass is going to have greater inertia. Well, the same thing happens in rotation. However, the distribution of the mass matters. And so the location of the mass also affects the inertia of that object. And so when we look at the moment of inertia, or rotational inertia, it is the tendency to resist angular acceleration. So if we want to find the moment of inertia of some irregular object, we can break that little object into really an infinite number of tiny little masses. And each of these tiny little masses will have a moment of inertia of mr squared, and it is the sum of this whole thing that gives us the moment of inertia. And so the sum of all that times the acceleration alpha will give us the sum of the net external torque acting on the object. And we can look at this as tiny little individual torques, that every little mass has its own little torque, and we keep adding it up into infinity until we have all of them added together. Or we can look at it as this summation equation. Now, with the irregular shapes, finding the moment of inertia is actually quite difficult. However, when we have nice shapes, we will have certain equations and certain formulas that we can use based off of calculus. We won't be doing the calculus, but we get those from calculus, and we can use those formulas for those nice shapes. And so we can define the moment of inertia as the sum of all of the little mr squareds. And this helps us with the Newton's second law of rotation, in that the sum of the torque is the moment of inertia times the acceleration, which this is very similar to what we had translationally, where we had the sum of the forces. We looked at the sum of the forces was equal to mass times acceleration. Well, this is the same type of thing. We have a force, rotational force, mass, rotational mass, acceleration, rotational acceleration. So really the blueprint here is no different. It's just we have different quantities now. They're all of our rotational quantities. One of the requirements here is that the angular acceleration is measured in radians per second squared. That is very important. So let's look at an example here, in that the moment of inertia depends upon where the axis is and how we rotate things. So we have two particles. Each have a mass of m and are fixed at the ends of a thin, rigid rod. So, well, we're not going to worry about the mass of the rod for right now. The length of the rod, however, is L, and we want to find the moment of inertia when the object rotates relative to an axis that is perpendicular to the rod at one end and at the center. So this one, part A, is showing us at the end. So when we rotate this around, we're rotating about a radius that is equal to L. Whereas when we have the axis directly through the center of the two, that radius is L over 2. And this radius here is L over 2. And so looking at the moment of inertia, we have to add up all the little masses times their radius or their distance from the axis of rotation. So looking at situation A, we have m1 times its radius squared plus m2 times its radius squared. Well, m1 is at the axis of rotation, so its radius is 0. That goes off to 0. Whereas r2 is at a distance L away from the axis of rotation. So we see that our moment of inertia here is ml squared. So this is a way for us to quantify its tendency to not want to rotate or not want to change its rotation. The same way that we use kilograms to quantify mass and translational inertia, we will use this, the kilograms times some distance, so a kilogram meter squared, and that will quantify the amount of resistance we'll have to a change in a rotational state. Now looking at part B, it's the same process, but what's different here is that now our radii are both L over 2. So when we put in L over 2 for each of these masses, we get L squared over 4. So we have an L squared over 4 here, L squared over 4 here, add those together, and we get 1/2 ml squared. So just looking at this, we notice that the rotational inertia, or the moment of inertia, is less in this situation than it is in this situation. And what that tells us is that part B, having the axis of rotation in the middle, it is easier to rotate this object when we rotate it about its middle, whereas it's harder to rotate the object when it is the axis of rotation is fixed at one end. This situation here in A is more resistant to change in rotation because it has twice as much moment of inertia. So all of our basic shapes are kind of summarized in this table here, and there's also another diagram on Schoology that you can download. But this shows us some basic shapes that we can rotate, like cylinders, cylindrical shells, rods either at the middle or at one end, spheres, spherical shells, rectangular prism, all that stuff. So any of these shapes, like for instance, if we have a cylindrical shell or a hoop, the moment of inertia is going to be the total mass of this object times the radius of that object squared. Now, if we have, that's if it's hollow on the inside. If we have it that it's not hollow, that it's solid all the way through, well, then we get a different moment of inertia. Just like with the thin rod axis at the middle, we get one moment of inertia, axis at the end, we get another. And so we have to use these appropriate to the rotation that we have. So let's look at an example here. And where we have a combined moment of inertia of a dual pulley of 50 kilogram meters squared. So we're told what the moment of inertia is. This is I. This is our I in our Newton's second law equation of the sum of the torque is equal to I alpha. The weight of the crate is 4,420 newtons, and the tension in the string is 2,150, or in this cable, I guess I should say. We want to find the angular acceleration of the dual pulley. Well, in order to find that angular acceleration, we have to look at what are all the torques that are happening on this pulley. So we look that there's this motor here that's pulling on the pulley here, and so that's causing a torque. And then there's also the tension force that is pulling down from the crate, that's causing a torque. And there's two other forces acting on this, in that we have this pushing force, or the normal force, from the pulley onto its support, and then we have the weight of the pulley. The nice thing about those is those are not applying any torque whatsoever, in that they have no axis of rotation. Their axis of rotation, the distance from the axis of rotation is 0. So we don't have to worry about those two forces in our torque equation, just T1 and T2. Now, in order to find T2, we can see that, okay, T2 minus the weight of the crate is going to equal our mass times acceleration, and we are accelerating upward in this case. So we see that looking at the sum of the forces in the y direction, T2 minus mg is equal to our acceleration. And looking at the sum of the torque on the pulley, we have T1 times L minus T2 times L2 is equal to I alpha, the moment of inertia, times the angular acceleration, which this is what we're trying to find. We're trying to find this angular acceleration. We're given everything except for this T2 here, and so we can use a little algebra to say that, okay, T2, solving this equation over here, is equal to mg plus m times the translational acceleration that we're calling ay. If we substitute that T2 in T2's place in here, that'll eliminate one of our unknowns, and so we're only left with ay as an unknown and alpha as an unknown. So using a little more algebra, looking at this ay here, we can get a relationship between ay to be L2 times alpha. Now, how do we get that? Well, that's looking at our tangential acceleration at that point here. Our tangential acceleration at this point here is just equal to alpha times the radius here. That's coming from alpha times r, where our radius is that L2, that distance right there. And so making that substitution, saying that ay in terms of alpha there, now we only have one unknown. We have alpha here, a little bit of algebra. We get alpha to equal that mess right there, plug in all of our unknowns, and we get an angular acceleration of 6.3 radians per second squared. And so this allows us to use Newton's second law. Instead of just having things in equilibrium where the sum of the torque is equal to 0, then the torque is going to equal some number, and that number is going to be the moment of inertia times the angular acceleration.